Okay, I think the broadcast has started. Welcome to your weekly webinar 3 with Michael Floyd. I'm your mentor and your mentee. You learn as much from me as I hope to learn from you. Now, just for quick starters, for one, the meeting with me that I requested for everybody to do, everybody has not done yet, but it's a form I need to fill out, introductory form that I'm hoping to fill out with everybody and also talk to everybody, make sure they are on pace with what we are doing. Also, setting the pace for this course. Like I said before, we are 33%, 30% done, pretty much. Let's not fall behind right now. Let's set the pace. I hope we are ahead on schedule. Like I said before, 30 minutes every morning, 30 minutes at night. And every time we spend, on the projects or on the classroom materials, if it's not too much, just write down on Slack, let everybody know, hey, I just finished this right now, more to brag and to also let your teammates know exactly where you are as far as your project. I feel like nobody is posting on Slack and trying to do this, either alone or only asking me questions and, just asking me questions as opposed to posting on Slack and asking everybody questions is not ideal. What I would prefer is I would prefer all the questions to be on Slack. Okay. And let's get this going. So this week's webinar is on perceptrons and gradient descent. And I will share my screen. Okay, my screen is shared. Okay, so perceptrons and gradient descent, they are both covered in this first lesson, which is introduction to neural networks. That is in the second part of the coursework. But, basically you have been over perceptrons before. Perceptrons were lightly covered and briefly covered in the supervised learning material in regards to classification. And as you can remember, perceptrons, what they do is they fit a line that displays whether the points are either classified as one thing or the other, right? And the reason why these perceptrons are so important, as you'll see later, is that you can connect and do plenty of other things with perceptrons in order to help classify the points or the inputs that you would need. So, and as we've seen before in the previous supervised learning cases, this is an example of higher dimension where you have 3 dimensions instead of 2 dimensions. And what you're doing even in multi-dimensional is you are trying to find a plane or a function that can split your data and classify objects based on the splitting of the data.
So let's recap. Information sign represent.
And this is how perceptrons are viewed as far as looking at them in a model. So what you have here, you have multiple dimensions, x1, x2, xn. You have your bias B, and those are all being fed into a perceptron. And that perceptron is then classifying whether based on the inputs, whether it is or it is not what the model is classifying. And the lessons give very, very great examples on and very great tutorials on perceptrons and neural networks and how everything works. And this is just a showing of exactly why they call it perceptron and why they call it a neural network. What happens is you are feeding information into the perceptron, or as you can see, it's very similar to how a nucleus would in a cell, like in your brain, how it would be very similar to how you are feeding information coming from receptors from other places, and then you are relaying that message. So that is why they call it perceptron and why they call it neural network, because it works very similar to a brain network. One second.
Now we finally have all the tools. Closer to our Miss class.
So this is the algorithm for the perceptron. And how you obtain the weights. You start with the randomized weights, and you use the misclassifications in order to slowly move the weights and the bias towards the best possible line that misclassifies the points, the least amount of points. As you can see, and then you keep updating this step. So you would update the weights, and as you continuously update the weights and the bias, you'd eventually get this line right here, right? And like I said before, this is your learning rate. But the main difference in the perceptron and what we need to accomplish with a neural network or a multi-layer perceptron is that we cannot have a discrete error function. So for what we just saw for perceptron, it only happens if it's correct. If it's not correct, what you are more looking for is an error function similar to what is shown on the right, where the error function is continuous and also continuous. So what you see here is that you know which direction to go off of the top, which the top is the most error. So you know which direction to go from the most error in order to decrease your error as quickly as possible. And so, as you can see, the error should be differentiable and it should be continuous. And a differentiable will help when we are trying to solve for the gradient descent and use back propagation, because with it being differentiable, we can better determine the error.
The prediction is basically the answer we get from the algorithm. A discrete f. Then to the red region are given very low.
So what you're seeing here
such as this point on the bottom is given a 20% probability of being.
The Perceptron has split the data, and instead of it being yes or no, similar to how we previously recorded, we now provided probabilities based on how far it is away from the line. For example, this point right here, it is very, very far away from the line, and it is also in the blue region, so it's 85% likely it is blue. So this point right here, it is very far away from the line, and it's in the red region, so it is even lower. It is 20% likely it will be blue, right? So if the line is 50%, the farther away going towards blue will make it higher than 50%, and the lower away, that means the redder it gets, would make it less likely to be blue, which we're measuring probability of being blue in this example. And in order to make sure, because we are, remember, just adding weights and bias, in order to make sure we have probabilities that are between 0 and 1, we do not have an activation function anymore to just say 0 or 1. We need a function that is continuous that will tell us whether a number is between 0, but that will give us a number between 0 and 1 based on our weights and bias from the perceptron. And that function is the sigmoid function. The sigmoid function is actually one of many activation functions that are used in neural networks. But the sigmoid function, as you can see, it's shown here, it relays a probability based on the weights and biases and the inputs coming into the perceptron. And so once we have this probability, we might have multiple.
Let's say we have a model that will predict if you receive a gift or not. So the model will give us predictions in the following way. 0 plus minus 1.
So once we have this probability, we will have multiple. Let's say we're classifying multiple instances, and once we have the classification numbers, whether probability or the outputs coming from the function, we need to then have a function that, based on the outputs from the perceptron, which could be in our case 2, 1, and 0. So the higher, because the duck has a probability of higher than 2 expected. Since the output of the perceptron is 2 for the duck, 1 for the beaver, 0 for the walrus, you expect the probabilities to all relay the same message. And we need a function that will take these outputs that we are getting and then create then we can create probabilities based on the outputs. And the output in this case, as you see for 0, 0 can give us problems because you don't just want the beaver to have 0 probability. And also, what if it was a negative number? So if it's a negative number, then that would also generate a problem because you cannot have a negative probability. So we need a function that will turn every number into positive, and that is the exponential function in this case. And as you can see here, this is how we use the exponential function. We take the exponential of what our outputs are from the perceptron, and then we sum up all of these and take the average. So we're not take the average and provide probabilities based on the amount that is generated from the sum from each classification. So here we have the duck is 2. We have the exponential of 2 divided by the sum of all the exponentials of the classifications that are in this problem. And so the duck is now 0.67, the beaver is 0.24, and the walrus is 0.09, with probability being duck, beaver, and walrus. And one-hot encoding. What we use one-hot encoding for is because in classification problems, you do not want to have something generated as...
all our algorithms are numerical. This means we need to input numbers, such as the score in a test or the grades. But the input, the variable for duck.
Our values for classification problems cannot be 1, 2, 3, and 4. The outputs that we want from the neural network want to be 0 and 1. So what we do is we have a neural network that then, based on different weights and the different y values we have. So instead of just having one column for y values, we would have 3 columns for y values, and those y values would be 1 and 0. So for this example, if it's a duck, we've given 1 for this column. If it's a beaver, 1 for this column. Walrus, 1 for this column, and it's zeros throughout. And so now we have 3 outputs that we are training to obtain, and based on the output, we then put that into the softmax function, and then from the softmax function, we have the probabilities that are generated.
Correct.
Now, where does probability and cross entropy come into play? So once you have the model and you want to determine exactly how well the model is performing, you can obtain the probability of, let's say, it being red, the probability of it being blue, and you're trying to compare 2 models. One thing that we usually do is the maximum likelihood, which is just find the likelihood of the model, which is it right here. But as you can see, these are only 4 points, and the likelihood can get really small in the span of 4 points. And when we are using hundreds of points, our likelihood function would then become very, very small, too small to be good to calculate on a computer or a calculator. So what we need is a function that takes what we have as far as product and turns it into sum. And what function does that? The logarithm function takes the products and turns the products into the sum. Because it is less than 2 or less than e or less than 10, it will be negative. 10 is usually used as far as the logarithm, but it really it's going to be, what you're really looking for is the error. So so we use the logarithm of the multiplication of the probability, the likelihood of probabilities, in order to obtain the entropy function. And so this is what it looks like. Because you're taking the logarithm, the product of the inside the logarithm is just the sum of the logarithms. So the logarithms all provide negative numbers. We multiply all these negative numbers by positive to get the entropy. And as you can tell, the larger the number is, the larger absolute value of the number is, that means the higher the cross entropy, and that means the worse the model performs as far as, and over here, the smaller the numbers are, the better the entropy. And now we have a look at gradient descent. So gradient descent is used to minimize the error function. So here you have the calculations, because it gets very dirty, not really dirty, but you need to use your calculus in order to find the gradient descent. But over here you can see that we need to know the derivative of the sigmoid function. And this is the sigmoid function, and the derivative is actually a pretty smooth function, just the sigmoid times 1 minus the sigmoid times 1 minus sigmoid function. So it's pretty smooth derivative. You use that for your error term. This is your error, which uses the entropy. So yi is 1 or 0 based on whether it is or it is not a part of, whether it is not classified as what you're looking at towards classification. And you have your probabilities provided here. And so this is the error function. And our goal for the gradient is to take the derivative of the error function with respect to each weight and respect to each bias. And that will tell us how it will change, of course, using a learning rate, how each point will change the, getting ahead of myself, how each point will change the weights and biases given how it is performed and given how far it is away from the line. So we calculate the derivative of the perceptron, or the output of the perceptron, with respect to the weight, because we have to use the chain rule in order to take the derivatives of all of the functions. So here is the final product. So you have the derivative of the error with respect to wj, and this is that. And as you can see, y is not affected by wj, but the y hat will be affected by wj. Same right here. And so we have 1 over y. This is the derivative of y hat with respect to wj. 1 over y hat. It does the same thing for this one. And now you need the derivative of y hat with respect to wj. And y hat, as you remember, is the activation function of your weights and your biases. And so we already know what the derivative of the activation function is. It is this right here. So we have the derivative of the activation function, and then multiplied by xj, which is the derivative of wx, or derivative of everything within this parentheses with respect to wj. And that is how this chain rule, that's how we get xj right here. And this is applied to, it's applied right here. And what you eventually get after you do your calculus and you simplify, you have y minus y hat times xj, the negation of that. And that tells you how your error, that's the change in the error with respect to the weight wj, which is highly affected by, well, which is affected by xj. So it's the same with all wj's and affected by xj, which is the input into the perceptron from wj. And for the bias, this is the term for the bias. So question, what does the scalar we obtain above signify? Closer the label to the prediction, the larger the gradient. So if the label is really close, that means the probability being 0.5 or closer, the larger the gradient, which you would think that the gradients will change a lot if the label is farther from the prediction, because the weight will have a bigger effect. So looking at the closer to the label is prediction, the smaller the gradient, and the farther the label is, the larger the gradient. The lessons do a very, very good job in covering all of this. And if you have any questions after, feel free to ask me. And this is the gradient descent algorithm. So you start with the weights, and then you iterate for each point. Just keep iterating until the error is small or your epochs are done, which epochs are the number of times you go through the algorithm. And you also usually run neural networks in batches. But so for each, for every point, for every or for every feature within each point, you update the weight, you update the bias. You're basically learning rate, and based on your y minus y hat, and then times xi, and then you keep going, like I said, until the epochs are done. And so now that you pretty much understand how a perceptron will work as far as getting the most accurate weights and biases, now it's time to combine multiple perceptrons to make multi-layer perceptrons or neural networks. And based on those neural networks, then you could do more cooler things with your model, like have more produce nonlinear functions, such as this function right here, by combining two linear models and activating them and then producing this output.
And
that's exactly what this does. So you have this model right here. And then the output from this model is multiplied by 7. You have this model output from this model is multiplied by 5. And you have -6 over here, which is just the bias term. And this is actually the model that is shown here. And so how do we get to these models? How do we find the weights when it comes to much larger neural networks? And the way we do that is through back propagation. So it's actually very similar to what we just did as far as our calculus in the previous lessons. What we do is we use the same rules, the same chain rules, in order to find the error, the differential of the error with respect to each weight. And once we have the differential error with respect to each weight, we can then use that in order to change the weights. And as you can see, it's the exact same thing. We have the chain rule of all of the functions. All right. That is it as far as gradient descent and perceptrons go. If there are any questions. Okay, the screen's back up. All right. So if there are any questions, I am available to answer questions. I can also ask questions, but I'm available to answer questions right now, and just posting questions. I'll wait for questions. Also, as a side note, I know everybody, it can be difficult to get everything done, but what I'm saying is I understand there's always a work-life balance, and now you have potentially work, school, Udacity, life balance that you have to encounter. But the time will run up. The 2 months that are left will run its course regardless of how you balance, and the way you balance will affect your outcome in the final 2 months. A better thing to do, I like to give examples instead of just preaching. So let me give examples of 3 students. Student A lives at home. He has no children, no job, no responsibilities. Other than getting his nano degree done, he has to make his decision on whether he should play his video games as opposed to studying for this course content. We all wish we could be student A, but we are more like student B or student C that I will provide the examples. Both student B and student C, they have full-time jobs, they have children, but one of them knows and prepares in advance to take this course and utilize his time and spend as much time as possible doing this course. So that means he downloads the lessons and he sneaks and watches the lessons while he's at work. That means he burdens the rest of his family with taking care of his children while he's trying to study for this. That means he might skip baths or skip hygiene, doesn't get haircuts, just use as much time as possible, perhaps a bath every other day, but uses as much time as possible and takes out as much time as possible in order to complete this program. and you have student C who knows it has the same obstacles as student B, but keeps up with his schedule, which of course nobody can blame him. When his wife gets sick and needs him to take care of duties that are opposed to her, right? He does those as opposed to his studies, and we will all encounter challenges, and I can understand how those challenges will arise and keep arising. But remember, you only have 2 months left, and I would like everybody to finish. So I do not see any questions still. I will give it a little more time. If you do have any questions, for some reason I can't see it on the chat, you can post them on the Slack channel as well. Or just state if you're watching it, just state on the Slack channel whether you're watching this or not. That will be helpful as well. Since we do have 20 minutes left, and hopefully somebody comes back and watches this, or if you're watching right now, you don't have any questions, what I will do is I will go through a little bit of the project. So that is what I want to do, just to try to get people started. So let me share my screen again. So here's the GitHub for Udacity's Data Science Nano Degree Term 1. You go to projects. Here's the first project, the charity, and the IPython notebook. So getting started, yeah, the 1994 U.S. Census data. You are trying to fit a model to the data, so this will be supervised. You want to predict whether somebody is making more than $50,000 or not. That's $50,000. People are more likely to donate to charity if they're making more than $50,000. And here's the first couple of lines. You're importing nappies, Pana, time. You're displaying it on the inline of the Jupyter notebook. You're reading in the census data from the CSV, and you're displaying the first column of the data in the pandas data frame. This is the first column. You have somebody who's 39 years old. I guess he works for the state, has a bachelor's, not married, but his income is less than or equal to $50,000. So we've read in the data correctly. And what we do here is what they want to see is the total number of records. So to find how many rows are in a data frame, it will be fairly easy. Just search Python rows in data frame, and that should give you a pretty good idea of how to find all the rows in a data frame. The number of records where an individual's income is more than 50,000. So what you are looking for is you want to split the data based on a requirement, and then based on that requirement or based on that condition, find the number of rows similar to what we did here. So you have Python, and what you want to do is split data frame by column value. That might give you an idea. Or instead of by column value, it could be by condition, similar to what I was saying right here. So you split data frame based on conditions or where the condition is true. All right, so the where function should give you a pretty good indication of how to do that. And the number of records where it's at most 50,000 and more than 50,000, similar things to do with those as well. Here are all of your classes for the data, whether they're continuous, and if they're not continuous, then you have the labels that are assigned within these sets. You're preparing the data. So now you have the splitting data into features and your target. So your income is what you're targeting, and your features is all the data, and except you're dropping the income. You're doing a log transformation in order to see which points are skewed within the data. You're then normalizing. It means making the data to be within 0 or 1 for all of the continuous variables. So when you're applying it to your supervised learning models, therefore the amount of the inputs or the weight of the input will not be highly affected by the size of the feature. One hot encode the features. I'm not sure if it needs a one hot encoding feature. I thought it was just more or less than 50,000. Yeah, so it's just 0 for less than 50,000 and 1 with greater than 50. So it's just going to be one Y column. And it tells you how to do that actually. Pandas get dummies, but this is going to input and output be one Y column. You're doing that for the income. You're printing a number of features. Oh, you're one-hot encoding the features. Okay, so for your uh, feature variables that are not continuous, you are one-hot encoding these features and then applying them into the model. So you're actually going to have a very, very large, high-dimensional feature in this thing. But this tells you how to do it right here. Pandas get dummies. And it's just printing the total number of features after the one-hot encoding. And your training, testing, split. You have your test size of 0.2. So you have 80% you're training on for your data, 20% for your test. So now you have 4. You have 2 sets. You have your training set and you have your testing set. This is talking about how you're going to evaluate based on the score. Let me check to see if I have anybody looking. No, nobody's looking as of yet. Nobody is talking in the group chat. Okay. So yeah, I'm not sure which exact supervised learning model they want you to use, but they want you to calculate the accuracy, precision, and recall, which are fairly simple to do. It should actually have sklearn functions that help you do all of the above, calculate the accuracy, recall, and precision. So, yeah. And so here's a function they actually give you. And I guess they help you, they tell you exactly what to do in the function. It times for you. Here's the learner that you're going to use. And you train the function, put predictions on the function, obtain the results, and yeah. And here you're doing it for 3 classification models. So it's just the number of samples for 1%. Then here you're just calculating, the length of the 1% and 10% and 100% of the training data. It's just the length times 1, 10, and 100%. Then you calculate the results of the classifier based on 1, 10, and 100% of the samples. That you're predicting. Yeah. it's pretty straightforward. This first project. So it tells you, if you read through it, everything. I've not read it through everything, but if you read through it, it will pretty much tell you all of these steps you need to take, and pretty much tells you exactly what to do and where to do it in order to make everything run and fit well. Yes. Oh, wait. That's something else. Excuse me. All right. So, thank you. I do not see any questions. Still not see any questions. Okay. So I will cut this to the end of the webinar. Like I said previously, tell your group leader whether you're on track or off track for this week. And also, please get everything done. And looking forward to helping you succeed in this course. Also, for this week, we should be finished with all of the lessons. And now what we're working on this entire week is completing this project. So let's complete this project. I think if you put in 30 minutes in the morning, 30 minutes at night, you should be able to complete this project fairly easy with 7 hours. And from that 7 hours, then having a complete project ready for submission on Sunday. Okay, let me know if you need any help with the project. I will be here. Thank you and peace.